All right, so we're back and now we're going to work on homework number 1, question 8. So here we are asked, okay, so we have an electron that's released from rest and within a uniform electric field. So the fact that we have a constant electric field tells us we're going to use a certain equation. That equation being delta V equals E D. Okay, and that only applies when we're in a uniform electric field. So remember, those words are a big hint that you're going to be solving this way. And we have the magnitude of the electric field. And we want to know the potential difference after moving 1 centimeter, and then how fast it'll be moving after it has traveled 1 centimeter. Okay, so I want us to remember that this right here is the voltage difference between 2 points. So we know it's at some rest and then it's released to 1 centimeter later. So we know what the electric field is. I think like 5.9 times 10 to the third. And then we know the distance it travels, which is 1 meter. Oh, I'm sorry, 1 centimeter or 0.01 meters. Convert that to meters. And at this point, you just solve. Okay. And that's your answer. Whatever this is, equals your answer. So I'll let you guys plug that in again. Sorry, I explained to online. I don't have a good calculator, and using my phone for these expressions was not awesome. Okay, so then in part B, we're asked for how fast it's going after it has traveled 1 centimeter. So we need to be able to find a velocity. And velocity as a variable is embedded in a kinetic energy, right? How fast it's moving, it's kinetic energy. What we do know, though, is electric potential. So electric potential, I'm just going to say, I'm just going to put PE. Remember, like this is always true. Kinetic always equals the potential. And that's equal to, some people write it as UE, but it's basically just electric potential, however you want to define it. And electric potential itself is equal to QV. I'm going to put a bar over this V so we don't get it mixed up with velocity, because kinetic energy, like something moving, remember, it's 1/2 mv squared, right? So you don't want to get these two V's mixed up. This is that potential difference that you just found, and this V over here is how fast it's moving. At this point, all you need to do, we're looking for a final velocity here. Coincidentally, this is the fact, like the question can be like, how fast will it be at its fastest? It's when all the kinetic energy is equal to potential. But I mean, this is just saying how fast is it after that point. So we just got to get velocity on one side. We still have QV, and then we're going to multiply by 2 to get rid of this 1/2, divide by m, and just square root this. You're going to solve for VF. You're going to get some value in meters per second. All right. And the only thing I want you to remind you of is, oh yeah, just keep track of what you're using SB. All right. So that's a quick question. I'll pause the recording and take questions. All right. I realized there was glare here. So here's the question in its entirety for you guys to see. All right. And now we're going to move on to question number 7. All right. This is homework set 1, question number 7. So here we're working with Gauss's law, and I already kind of drew the diagram we have here. So I want to say by nature of the question, because there is no charge enclosed inside the sphere, the total flux is equal to 0. So that means we can just easily define like the flux total. So flux, I'm just going to call it total, as equal to the flux on the flat surface and the flux on the curved surface. So I'm going to say is equal to the flux on the curve plus the flux on the flat. Okay. So with this equal to 0, we actually can rearrange the equation where, they're both equal to 0, right? So one of them is going to be negative, one's going to be positive. All right, so that's equal to 0. I'm just gonna leave it there. I don't want to continue that avenue. All right, and for a non-half, I have my notes on my phone here. For a non-half sphere, which encloses the charge Q, by definition of Gauss's law, we know that the flux, this is part A, the flux of the curved surface is going to be equal to Q over E naught. The important thing to note here is, since it's only half a sphere participating with the charge at its center, the flux is also half. So it's just over 2, right? That's half of the sphere. All right. And then that brings us to the point of the normal vector. So here we basically have a field pointing through the flat surface and out there. So what's a normal vector? It's basically a vector that's perpendicular to any point on this surface. So perpendicular is 90 degrees, so it's going straight out. So when the vector is escaping the Gaussian surface, it's always positive. And that brings me to my next point, which is over here. The vector itself is also, the normal vector is also entering here. And because it's entering, we're going to say Q of the flat surface is equal to minus Q over 2E naught. All right. And that's the answer for both of them. So the point I really want to stress here is this positive is the result of the normal vector escaping the Gaussian surface. And this negative right here is the result of it entering the surface here. It's kind of hard to visualize, right? But although the vector does go all the way through, initially it first has to enter, right? It enters and then it keeps going and then it escapes right here. All right, so that's how we know it's going to be negative and positive. I think that's that.
Quick question. How did you know that the total flux was 0 again?
So we're back with the same question, number 7. I just want to really stress this point. We kind of talked about it afterwards. Because the charge is not enclosed in the surface, it's like hovering right above it, the total flux is equal to 0. And I'm going to use the same words I did before. If you don't believe me, just look at the proof here. Here we have Q over 2E naught minus Q over 2E naught. So when you add these two together, they're both going to cancel out and equal to 0. I apologize. Someone keeps opening the door. Let me check. Yeah, apparently like a club thought they had a meeting in this room. So every 5 seconds, a group of students walk in. So that's mildly distracting. Anyway, yeah, so the charge is floating above. And another student brought up a point which was, how come in the in-class example, when that it wasn't equal to 0? And that's because if you read the question closely, the charge itself is actually within the Gaussian surface. It's like embedded inside the sphere. And you're asked for the field or whatever it was at a point outside. So here, the difference is the charge is outside, the total equals to 0. All right, that's that question. All right, the next one we're going over is homework set 1, number 5. So this one is just plugging into our kinematic equations. And we have a proton, it accelerates from rest in a uniform electric field. So that the fact that it's a uniform electric field is necessary when we're applying kinematic equations. At some time, its speed is given non-relativistic because v is much less than the speed of light. That's a little caveat that will become important to the end of the semester. And let's just worry about part A, which is the acceleration. So this is just application of an equation that he gave you. It's also on our SI worksheet. So it's equal to Q big E divided by the mass of a proton. And mass of the proton is something that either needs to be memorized, or if it's included on the equation sheet, lucky you, you don't need to memorize it. And other than that, the Q of an electron the charge of an electron should also be memorized, and they give you what the electric field is. So just plug everything in and you'll get A. Let's move to part B. So in part B, we're asked how long it takes to reach this speed. So we need to find a time. Which kinematic equation should we use? You'll see that it's VF, and I'll explain why, equals V initial plus the acceleration times time. A few things directing me to use this one. First is we're looking for time, so we know time is in the equation. Also, they told us that it starts at rest, so that is equal to 0. And secondly, we just solved for acceleration, so we have enough to incorporate acceleration. Oh, and we're also given the final sometime later what its speed is, right? So VF over A is going to be equal to T. You just bring your A down that you solve for and solve for, plug it in there. And then in part C, we're asked how far has it moved in this time? Now, using this time, we can calculate the displacement from the initial to the final. All right, so which equation should we use? Again, I'll explain why it's this one. Minus I naught equals 1/2 V initial plus V final times time. All right, I know I can use this one because first we're looking at the position it has moved in this time. So we know where it needs some displacement. We also know that the initial velocity is equal to 0. So that pops out. We just, we're given the VF and we just solve for T. So at this point, we can solve as we know it starts from that initial position 0. So we can just pop that out to 0. And XF is going to be equal to 1/2 VF times T.
Should it be negative VF?
No. Why would you say negative VF?
Since it was VI minus VF, I didn't know if it should be negative.
No, that's
Instead of
plus.
VI.
Oh, can you not see plus?
Oh, I'm sorry. Okay, thank you. That makes more sense.
Sorry, my iPad stopped working, so I'm trying to use this classroom Zoom arrangement. It's not great. I'm gonna try to get a new iPad, but it's very expensive. So
Yeah, no, it's working well. I just missed that. Thank you.
oh, you got it. And then we're asked for what's the kinetic energy at this time, right? So we have kinetic energy. It's going to be kinetic energy at that final position. It's going to be equal to 1/2 the mass of a proton times that VF squared. All right. And then you just plug everything in and you will get some number and your units joules, right? So make sure you choose all the right units too. So that's going to be like meters per second squared. It's going to be seconds. Here it's going to be meters, and here it's going to be joules. Other than that, I'll leave all the fun of plugging into your calculator for you guys. Number 5, done.